Alright, in this video for week 6, we're going to go ahead and take a look at a new test for categorical variables called Test of Independence. A test for independence is sometimes also called a test for association, and it's used for claims about two categorical variables. And test for independence, what we are looking for is a relationship between those two variables in a single population. So one easy way to identify a test for independence is two different variables, but one population. Much like the other cases we've seen this week, we are going to be using the chi-square distribution. And you'll notice state plan do conclude looks very similar. The state, we're doing the same thing. We're defining the variable's interest. We're putting our data in a table. We're calculating expected. For the plan, we're identifying our test and doing the same check. All expected are greater than or equal to 5. The do, we're calculating our test statistic and p-value, and we're drawing and labeling our shaded chi-squared curve. Conclude, we're doing statement about the null, statement about the alternative. A couple of small changes. Because we're comparing two categorical variables in the same population, our observed is going to be in a two-way table. So the entire table is going to be observed values, all of the rows, all of the columns. And I'm going to then have to calculate expected frequencies for every box of the observed frequency two-way table. The formula for that is right here. Row total times column total divided by table total. And I do that for every box in the table. The downside is the bigger the table, the longer this takes, and it gets really tedious really fast. The upside is we live in 2025. I don't need to do this. My calculator will calculate these for me when I perform the test on my calculator. So these tests for independence and the tests in our next video, we're actually going to do the do step before we finish the plan step, because the do step is going to give us these expected values, and we then can check that our expected frequencies are 5 or bigger. You'll notice the formula for our test statistic is the same. Observed minus expected squared divided by expected. Add them up for every box in the table. Our degrees of freedom is slightly different. Because I have two categorical variables, my degrees of freedom is now rows minus 1 times columns minus 1. So categories minus 1 for the first variable times categories minus 1 for the second variable. On your calculator, things are going to look a little bit different because now my observed is in a two-way table and not a simple list, meaning I need to enter a two-way table into my calculator. And we do that using a matrix. To do this on the TI-84, you're going to press second and x to the minus 1. Second, x to the minus 1, you'll notice above that it says matrix. And you're going to move over to edit because we want to edit a matrix. And when we press edit, it pulls up matrix and it asks us how big is it. So you enter the number of rows first and press enter, and then you enter the number of columns second and press enter, and then it gives you a blank table and you're going to enter the data row by row. So 1, enter, 5, enter, 3, enter, 2, enter. And each time you press enter, it's going to move you sideways. Once that first row is done, it's going to move you to the second row. And it'll keep going all the way through until your entire two-way table is in that matrix. To get back to the home screen, you would press second quit, and then you can start calling up the function that we're going to use to run the test. In GeoGebra, it's a little bit easier. GeoGebra treats a matrix or matrices as a list of lists. So you're going to make curly brackets for the entire matrix, and then curly brackets for the list for the first row, comma, curly brackets list for the second row, and then if there's more than 2 rows, repeat until all of the rows are in your list of lists. Once we've done this, we're going to pull up our stats test menu, and we're going for chi-squared test, not chi-squared GOF, chi-squared test. And it's going to ask you 2 questions. Where did you put your observed? Where do you want the calculator to put the expected? And if you consistently put your observed in A, you should never have to touch anything in this menu. You just go down to calculate, and the calculator will run all the calculations for you. On GeoGebra, you set up your matrix just like we explained on the previous slide. You go chi-squared test, and you feed it the name of that matrix. It will recognize that you've given it a single matrix instead of 2 lists, and it will perform the test appropriately. GeoGebra figures out what test you're doing based on the format of the input. Whereas the TI-84, it needs a clue as to what type of test, and then it knows what input to look for. Okay, so let's do some examples so we can see what this looks like in practice. So example 1 says De Anza College is interested in the relationship between anxiety level and the need to succeed in school. A random sample of 400 students took a test that measured anxiety level and need to succeed in school. The table on the right shows the results. De Anza College wants to know if anxiety level and need to succeed in school are independent events. So a few things. First, they were really nice. They put the observed values into a two-way table. So all of this data from here down to here, that's my observed. They also ask me if anxiety level and need to succeed in school are independent. They're asking me to perform a test for independence. They didn't give me a level of significance, and I know my default is 5%, 0.05. So I know that I'm looking at anxiety level versus need to succeed in school. My null hypothesis for a test for independence is the 2 variables are independent. And the alternative is that they are dependent. So the assumption is there's no relationship between the 2, and then the alternative is there is a relationship. We are doing a chi-squared test of independence. And I know that I want my expected values to all be greater than or equal to 5, but I don't know if that's true yet, because I am going to run the test on my calculator first. So chi-squared test, and then observed is going to go in matrix A, and expected, I want the output to go in B. That's our default. And that's going to spit out a test statistic, and it's going to spit out a p-value, and it's also going to spit out the expected matrices, or the expected values in a matrix, in matrix B. So let's go ahead and do that. We know to enter a matrix, we go second x to the -1. We go to edit, and then we tell it the size, and it wants rows and then columns. I have 3 rows and 1, 2, 3, 4, 5 columns. So 3, 5, and then I'm entering row by row. I double check that matrix matches my two-way table. So I'm going to go back to my home screen. I'm going to go to Stat, Tests, chi-squared test, which is option C. And it's already set up. Observed is an A. I want expected in B. I'm going to run the test. And I'm going to copy down this information, and then I'm going to check that my expected value are all bigger than 5. So 48.4, and a p-value that is approximately 0, because that's 8.2 times 10 to the negative 8. That's really, really small. That's basically 0. They're also telling me my degrees of freedom is 8, and that checks out. 3 minus 1 is 2. 5 minus 1 is 4. 2 times 4 is 8. So that does match out. To pull up the matrix I want to view, I'm going to go second matrix. I'm going to go over to edit, and I'm going to pull matrix B, and you'll notice A and B are the same size. That's a good sign. And I just scan the rows and columns and make sure everything's bigger than or equal to 5. And they are. So we can come back and check that off. If you wanted to be extra studious, you should jot those down in a different color here. You can round to the nearest whole number if you want to be lazy, just because you run out of space if you don't. I'm going to do that really quick. To do our conclusion, we take a look at our p-value and we compare it to our alpha. 0 is much less than our assumed alpha of 0.05. And when p-value is low, we reject HO. So we are going to reject the null hypothesis. So we would say because our p-value of approximately 0 is less than our level of significance of 0.05, we reject the null hypothesis. We have significant evidence to support the claim that the anxiety level and the need to succeed in school are dependent variables or dependent events. All right, let's go ahead and try a second one. So second example says transit railroads is interested in the relationship between travel distance and the ticket class purchased. A random sample of 200 passengers is taken. The table on the right shows the results. The railroad wants to know if a passenger's choice in ticket class is independent of the distance they must travel. So again, that last sentence gives me a clue of what type of test I'm doing. If a passenger choice in ticket class is independent of the distance they must travel. At no point did they give us an alpha, so we're going to assume a level of significance of 5%. And I can see here a two-way table. So this table represents my observed values. I'm going to go ahead after we do the test and write my expected in a different color. So the two variables we're looking at are ticket class versus distance traveled, or travel distance. Our null is that these variables are independent. So no relationship. And the alternative is that they are dependent. There is a relationship. Dependent. I know how to spell. No, I don't. My poor little brain. Dependent. We are doing a chi-squared test for independence, which means we need to check that our expected values are all bigger than or equal to 5, and that's something we're going to do after we run the test. On our calculator, it's chi-squared test, and then the observed go into matrix A, our expected go into matrix B, and that's going to spit out our test statistic and our p-value. It's also going to spit out our degrees of freedom, and we should check that it gives us what we expect. I see 5 categories for distance traveled. I see 3 categories for class. So 5 minus 1 is 4, 3 minus 1 is 2, 4 times 2 is 8. So I expect that if my calculator did this correctly, I should get a degrees of freedom of 8. Let's go ahead and get our data in a calculator. Second, x to the minus 1. I want to edit matrix A. In this case, I have 5 rows and 3 columns. And I'm just going to type over with the new data values. From here, I'm ready to run my test. So stat, tests, chi-squared test, A, B, calculate. And we get a test statistic of 15.9 and a p-value of 0.04. And I forgot to draw this in the last one. I really should draw this. That's why I need a live audience, so you guys can catch me on these things. So we know our chi-square distribution is skewed. We know we're pretty far out in the tail at 15.9 when our mean is 8. And that area there is our p-value of 0.04, or about 4%. I am going to go back and check that my expected turned out all right. So second, x to the minus 1, and I'm going to view matrix B. And the smallest box I see in my table is 6.6. So we have cleared that condition that our expected values are all bigger than 5. From here, we can go ahead and draw a conclusion. Our p-value is less than our alpha, and when p-value is low, we reject HO. So we are rejecting our null hypothesis. Because our p-value is less than our alpha, we reject the null. Therefore, we do have sufficient evidence to support the claim that the variables ticket class and distance traveled are dependent. There is an association between those two. All right, if you have any questions on tests for independence, feel free to send me an email or drop by office hours. Otherwise, I'll see you in our next video.